Welcome to this introduction to DNP3 protocol. We're going to be discussing some of the philosophical things about DNP3, making it work on an RTU32M and connecting it up to ClearScader. Let's just look at a few points of interest. DNP3 has been around since late 1993, once a user group took hold of the protocol. It's dominant in the power industry in North America, but strong market acceptance in power, oil, gas, water worldwide. Importantly, it's an open and public protocol. Why are we using DNP3? Obviously demand for faster response times, interoperability, more recently security. But in addition to the definition of the protocol, the format of the messages, there's a communications philosophy. So what will be included in the message? When will it be sent? How is it prioritized? What are the security methods, etc. And how do we transfer data with DNP3? Well, first there's the static data polling method, the concept of requesting all of the current data values, termed a static poll. There's also event polling, where the master is able to request unread events, and there's also the ability of the outstation to unsolicit messages. Remember, events are buffered by the slave until they have been successfully read by the master. So an unsuccessful read, if it's not ACT, the events stay in the slave device. And events can be separated into three classes. The classes can be used however you like, but typically Class 1 is considered the high priority events, Class 2 is medium, Class 3 is low. But some industries, some regions, some particular customers might even decide to use Class 1 to differentiate between analogs and other point types, or between system alarms and system events. When the master polls the RTU for events, it's able to request all classes or individual classes, and it can be in a single query. There are 5 different object types: binary in, binary out, analog in, analog out, and counters. And for each type, there's an address range of 0 to 64,000. Different variations, so with and without status information, with and without timestamps, and there's even different formats of an analog value. For example, as a 16-bit integer, 32-bit integer, 32-bit or 64-bit float. And an important feature is file objects and also even vendor objects. So we said before about the concept of static data and event data. When the host is requesting static data, it issues a class 0 poll. So that requests all static data. So the RTU must reply with all of its DNP points. Class 1, 2 or 3 poll is a request for event data. Typically when we look at how does a DNP master manage its messaging, you'll find that it is regularly issuing event polls and less frequently issuing integrity polls, which are a combination of events and class 0 data. Now we're looking at an example of a water system and a wastewater type application, particularly in older systems with slower digital data radio networks, where there may even be 40 to 50 RTUs sharing a communications channel. The benefit of having DNP3 is the overall system response can be better than 2 seconds. So we receive alarm data fairly quickly, we issue commands fairly quickly, and because all of the data is time-stamped and we're able to unsolicit the high priority events, we have a very nice quick system response. So in these types of systems, the master might poll the slave RTU anywhere between every 30 seconds to every 10 minutes, but typically requesting event data, so unread events, and less often it would request an integrity poll, so it would also get the static data. That leaves plenty of free time for important alarms to be sent unsolicited by the slave. A little note here about and when event data is uploaded, it actually includes things like the pump stop and start times, level measurements. It allows the historian to backfill the trend data with what's termed time of occurrence rather than when it was received by the SCADA host. So we can recover from comms failures, but best of all we have system-wide accuracy, very good for allowing analysis of data from different sites. And here's a look at how does an RTU implement DNP. Typically a points table is used to list all the DNP points of interest, segregated by their point types, so their digital ins, their analog ins, digital outs, etc. Each point has a DNP address. Obviously it must also have the static value, so that when a class 0 poll occurs, the RTU can reply with the current state or the current value in the case of an analog. So when the master issues that class 0 poll, the slave device will go look in its DNP table and it will respond with all of the values. They are not having to be contiguous, so you could have address 0, address 10, address 100. The RTU would have to retrieve that data and reply, and the reply includes the address as well as the data value. So it's not just position-based data. Now we're looking at the concept of event data. So the DNP table not only contains address information, it also has information such as the point class and the event reporting rules. How long must a digital value have changed for before it becomes an event? Or how much should the analog value have changed before it's considered an event? So in an example here we're showing some debounce on the digital points. We're showing some thresholds on the analog points so that the RTU is watching its static values and determining should it create events. So we make reference to the idea of the events living in a bucket. So the RTU's job in life is to monitor the points. If it sees that a point has breached any of the event rules, then it simply puts an event in the bucket, either waiting for the master to read those events or watching to see have the unsolicited reporting rules been breached. Should I unsolicit some or all of this data? So here we're showing the idea that the three sort of message transfers: the master requesting static data, the master requesting unread events, and the RTU having the ability to unsolicit events. And the idea of unsoliciting events is maybe it's watching the class 1 events. As soon as a class 1 event occurs, it may unsolicit. And when we look at the messages themselves, we see that a DNP message is significantly more complex than a Modbus type message. Interestingly, they can vary in length and may even have multiple messages. So the master might send a single request, but the outstation RTU may in fact respond with multiple messages. And the messages can be quite large. So a little note at the bottom here: if the slave RTU has a lot of unread events, a single query can result in multiple responses from the slave to offload the events, and they are offloaded newest to oldest. The master does have the ability to limit the number of events. It may want to come around again later and retrieve the rest of the events. A little look at the format of the messages, the concept of message headers and data. There's a lot of information in a DNP message header. So here we're showing a little quick overview of the message header. And when you request say class 1 events from an RTU, the message header may still include information that this RTU has some unread class 2 and class 3 events. Or in the case of the RTU wanting its clock to be synchronized, it would set the flag to say clock synchronization needs to occur. The master is obliged to then sync the clock. Another important feature is the device restart. Anytime an RTU restarts, it leaves its restart flag set until it's talked to by the master, which must then reset that restart flag. And there's other message flags in here, such as parameter errors or the fact that the event buffer may have overflowed. And another interesting one in the bottom here is config corrupt. So we have systems deployed where the master station is looking for that config corrupt bit, and it may use that to trigger the downloading of an RTU slave configuration. Here we're looking at data quality. This is of the points themselves. So not only does a binary point return its status value, but it also returns some point quality type information, and similar with an analog value. So we can do things in the RTU32M, for example. When we detect a loop break on a 4 to 20 milliamp input, we can flag that as one of the quality bits. Or if the module was to be removed, we can flag the COM lost bit. So in conclusion, we say DNP is more than a protocol. There's a range of benefits: improved system response times, accurate system-wide timestamps, communications fault tolerance, and the event process means the RTU is effectively a data logger. And the event classes can be used to allow prioritizing of unsolicited messages. And best of all, for the users, it's an open protocol, so it allows vendor independence. Thank you. Now we're going to configure our RTU32M. We start up our work suite, and we're going to open up make a project list, put it in my training location, and I'm going to call it DNP Training 1 will do. And so now we have a new workspace. We don't yet have a project, so let's add a new project. Call it DNP number 1. We will accept the default. Happy with the function block diagram. We'll be using recipes. We could choose our protocol at this point, DNP3 slave. We're not doing any binding. And we've now created an empty project template. If we look in the main program, there's nothing. If we look in the profiles, we can see that the profiles, there's nothing configured at the moment, but we're going to be using the RTU DNP3 slave protocol. If we look in there at the moment, we see there's nothing configured. So what we'll do first is just create a few variables. So we can right click on the variables heading. We can add multiple variables. I'm just going to make a few binary input variables by entering %, 0 to 3. We're going to replace the percents with 0 to 3, so we're going to make 4 variables, bin 00 through to bin 03. We're happy that they're booleans. We say create. We will make some binary outs while we're here. We will make some analog ins. We'll make those as reals. And we'll make some analog out as well. And if we have a look over here in our list of variables, we can see that we've made some binary ins, binary outs, analog ins, analog outs. If we went to the DNP table, we could drag all of these variables into the DNP table. By default, it made them all binary ins. We know that these ones, using shift and double click, change them to binary outs, analog ins, analog outs. And I'm going to iterate their point numbers by 1, starting at 0. So we have 0, 1, 2 and 3. We'll do that for each of those. suppose I could just type them in manually. So at this point we have a DNP table that has 16 variables, 4 of each type, each with a unique point number. And let's play with some event classes. Just to make it easy for us, we'll make point 0 use class 0, meaning there'll be no events, just a static value. We'll make point 1 use class 1. So I'm going to do that for each of these points, just to play with their event classes. Things will make a little more sense when we connect to our SCADA host. Hopefully we got that right. I'm going to accept the defaults for the static and the event variations, and we're going to look at how those are set up later. I'm not going to put any debounce on my digitals, but I will put some thresholds on the analogs. Otherwise we could potentially be making lots of unsolicited events, as the analog values might bounce around if we were to associate them to some physical hardware. We have some different modes of thresholds. So if we just go back and look, we see that we have no threshold, scaled value, measured value, absolute value. If we start with absolute value, then that's how much the value must change. So if we say we have an absolute threshold of 15, then the value must change by 15. If we say that it's of the scaled value, then we must associate a scale to this point. And if we associated the scale as 0 to 100, and we said that the value that it must change is 5, then it would be 5% of that scaled value. If we do measured value, we still put a scale in, and when we say 5%, it will be 5% of the value at the time. So if we had 0 to 100, but the value was, say, 20, and we had our threshold set for 10, then it would be, what is 10% of 20? So the value would have to change by 2. So that's just things to read up about, how we do our scaling. So we've set absolute value, so we need to find the absolute threshold, which is here, and I'm going to say that our value must change by 10.0 before we are going to make an event for any of those analog in or analog output points, and that will be enough for us to say that we've now built a DNP points table. Now, we're not quite ready to connect to our SCADA host, because at this point we've only defined some points within the RTU. If we go here to the field bus configuration, earlier when we created this application we said that we needed a DNP slave, but all we've done is effectively invoke the DNP3 slave driver. If I right click on this, I need to insert a port. And for my testing now, we're going to do a quick TCPIP example, and we can accept the defaults. We're using Ethernet TCP, we're using the DNP default port number, which is 20,000, and we're using the default mode, which is listening. There are different types: listening, initiating, and dual endpoint. If we're a listening device, then we wait to be connected to from the SCADA host, and we then learn of that SCADA host IP address, etc. If we're initiating, then we would have to have put the master's IP address and port number in this field here, because we couldn't initiate a message without knowing who to have the conversation with. But by default, by leaving it in listen mode and listening on port 20,000, we are going to listen for a master to talk to us, and after that we will learn the master's IP address. So let's accept the defaults, and we need to also insert a slave. The default session ID first session will be 0. I'm going to make this slave address 100. I'm going to communicate with a master 101. I'm going to accept the other defaults, So at this point we have a configuration basically ready to play with, but there's a few application layer settings. If I click on this heading here, there's quite a lot of information in here termed the application layer settings, such as what is the default. So when I created points back in the profile over here, we actually gave each of our points an event class. But if we didn't, then based on their point type, they would be given this default event class. And we can also set up the default variation. So this is the static and event variations for the points. So by default, my binary inputs are what's termed packed format. I'm going to change mine to be with status flag so that my binary points have their status information. My binary input events, I can have without time, absolute time, or relative time. I prefer absolute time. That's a timestamp of when it occurred. A relative time is the time since it last changed. We have binary ins, we have binary outs with status. I'm going to have timestamps also on my binary outs. We have not configured any counters yet. We're going to have analog ins. We are going to use a floating point value, and we would like our floating point analog value to be with time, and we want to do something similar for our analog output as well. So we've got our analogs as floats by default with time. We're recording all binary events. We are going to record all analog events, and here's control for the size of the event buffers. For our demo here, we're going to make the buffer size a little bigger, 1000 binary input events, 1000 analog input events. Unsoliciting is allowed. Got our default retries. These are the triggers for sending unsolicited messages. For the purpose of our demo, I'm going to set the class 1 events to unsolicit as soon as there is one unread event. I'll leave the class 2s at 5. I'll stretch the class 3s out to 10. I'm going to wait no seconds. So when a class 1 event occurs, it's going to be immediately unsolicited. At the moment, there would need to be 5 unread class 2 events, or any class 2 events older than 5 seconds. I'm going to stretch this out to 15 seconds. And I'm going to stretch this one out to 50 seconds. So that when we are playing around with our connection to the SCADA host, I can make things change in my different points, and we'll see different behavior as to when points are unsolicited. So the concept here at the moment is class 1 events are sent straight away. Class 2 events, there's either up to 5 unread events, or any of those class 2 events are more than 15 seconds old, we will be unsoliciting them. Now in a normal system, these figures are much larger. You would be holding your class 2 events for probably as long as the standard poll time, so that normally your class 2 and class 3 events are being picked up by the event poll from the host, and it's only if something untoward was to occur, which might be based on quantity, or that the host was delayed in polling, that you might consider unsoliciting them. Everyone gets excited by unsolicited events and think they can speed up their system and send everything unsolicited, then have lots of message collision avoidance type issues to deal with, so you're better to start slowly. But we're in demonstration mode here at the moment, so we're going to make things look fairly snappy. So this is where you put your tongue out to the left. First of all, we're compiling the code. We want to see that there was no error detected. We'll go online to the RTU. It's already got an existing application, so I need to stop that logic application. I download the application, and I want to see in here that things are okay. I can see that I'm using slave address 100, master address 101, and a little note here to say configuration file not used, meaning we're not using the web-based interface. We're taking all of our information from this logic interface. So before we connect to the master station, let's go into our main program and let's add some DNP3 status information. So let's add some information about our events. We can have a look and we can see have we got any unread DNP3 events. Oops, we have to go to the right place first. We have to go to RT32 DNP3 and we choose the events block. Oops, we're in run mode. We need to be offline to the RTU to add a block like so. I'm not going to configure the points. I'm happy to look at the status of the block when it's running. We'll highlight it and we will just pretend we have some variables by looking in the block, and I'm going to make that always on by making that true. We've associated our slave to session 0, and if I wanted to reset the events, I could trigger this tag. So that will be enough for us to see are there any unread events by their point type and also by their event class. Now we have some other interesting information in here, such as we can watch the session and we can watch the channel. I'm just going to drag in a session status block for the moment. Again, I won't build the output variables, I'm just going to monitor this. Come on. We will get those statistics populated in here for us. I do want this to be true. The ID that we are using, and we'll put this into this RTU. Now I think I actually have my ClearScader host active at the moment, so I'm just going to shut down that server. And what I'm interested in seeing is if I went to my global variables and I turned on this binary point, I want to see, does it create an event? And my expectation is that when I change something I see a result. Why would binary input 0 not create an event? There is always a reason. Binary input 0 has been set to not create any events. So if we want to see an event get created, we need to change the state of binary input number 1. So let's do that. So this time when we change the state, we see there is a new binary input event and it is a class 1 event. We change the state of the next channel, there's a second binary input event and there's now a class 2 event. So we see that we are creating binary events. Can you remember the rules that we put in for the analog value? We said the value had to change by 10. So we said that any analog input, remember we'll use analog input number 1. Over here we set it as using absolute value and we said the value must change by 10. So let's go to that analog value and we'll change it by 9. Again, you cross your fingers and you hope that that didn't create an analog event. So we have a look in the list, yet there hasn't been an analog event. But if I was to go 10.5, the expectation is there's been an analog event created. And we said that one was a class 1, so there's been an additional class 1 event. Let's make it 22. And there's been an additional class 1 event. Go to the next channel, as long as we make that more than 10. We expect there to be an additional analog event and now an additional class 2 event. So at the moment our event buffering is looking like it's working in the RTU, and I'm going to enable my ClearScader server, and I'm also going to turn on Wireshark. So I'm going to use my local connection. I'm starting Wireshark. I am going to put in a filter. I'm just watching IP address. This is the IP address of my slave, and I'm going to use the DNP3 protocol. And here we can see that my SCADA host just did an integrity poll. It read class 0, 1, 2 and 3, and it received a response. This time it read just class 1, 2 and 3, and it received a response. So we'll just see what the pattern is here. So I can see, looking at this, that every 10 seconds we are issuing a event poll, and every 30 seconds, so that top of the minute and at 30 seconds past, we issued a class 0, 1, 2, 3. So let's have a look at the response to a class 0, 1, 2, 3. If we look in here, we will see the Wireshark has decoded the message for me. It's saying that there were 4 different object groups: binary in, binary out, floating point in, floating point out, and each of them had 4 points associated to them. And when we look at point 0, 1, 2 and 3, we see that point 0 is off and point 1, 2, 3 are all on. And who can remember what values I put into those analog points? So 22 and 11. If we sneak a peek back at the RTU, maybe we just shrink this down a little bit. What we want to see is that currently we have the first binary input is off, the next 3 binary ins are on, and our analog values are 0, 22 and 11. And here we're looking in the messages of Wireshark. We can actually see those same values were reported to the SCADA host. And even though the SCADA host requested static data and event data, there's no event data showing in that response because there were no unread events in the RTU. If we have a look in ClearScader, if we look at the outstation that's been associated to this and display points, then we can also see that we have obviously some alarms. We'll just acknowledge those alarms. I thought my security level was sufficient to do that. We can just do them individually. So here we can see the values in ClearScader. Now remember, we said that our class 1 events were going to be reported straight away. So expectation is if I was to watch this binary point here and I was to change the state of this point here, then we straight away see it change in ClearScader. I'll change it again in the RTU, straight away we see it change in ClearScader. Now let's have a look at Wireshark. Why did we see it change? Because there was some unsolicited messaging occurring. So here is an unsolicited message saying this is a binary input change with time. It tells me that it was point number 1 and it became a value of 1. So I look back in my RTU at some point, I changed that. Let's change it back again. Now let's look in here and find that unsolicited response, and this time I change point number 1 to 0. We see the timestamp. This is in UTC, so it's 1641 in Australia at the moment, but 0541 is a UTC timestamp. So important when you're trying to understand what's happening with your DNP3 that you have to look at sometimes both ends. So we're looking at the host end of things here. We're looking at the RTU end here, and we're using Wireshark to sneak a peek in the middle. Remember, the RTU also has the capacity to, if I log back into this RTU, the RTU has a packet capture facility that I can ask the RTU to capture packets for me. So I've asked the RTU to start capturing. If I was to make some changes to these points, change that analog value, and now I'm going to stop capturing, and the RTU has a file ready for me. So we'll download that file. We want to open it with Wireshark. And I'm going to apply the DNP filter to it. So the RTU actually captured this little sequence of messages for me. It captured the host requesting class 123 data, and the response from the RTU at the time was, I have no data. Oh no, there was one. There was a binary change in the RTU. And there was also an unsolicited response, so I must have changed the analog value as well as the binary value. And then we also happened to capture a request for class 0123. Looking at that response, there was just the static data again, so showing me those updated values. Again, sneak a peek back in the RTU, we can see that we changed the values to 5 and 11. But this time that was captured by the RTU and displayed to us. So I'm going to stop Wireshark, just maximise this again so we get a better look at what's happening in the RTU. And this time we can see that there are messages being sent and received. If we just wait here for a sec, remember every 10 seconds we saw that the SCADA host was requesting data, so we just see messages received, messages sent. Wait another 10 seconds. We see things occurring. If I was to change the state of this analog value, make it 50, then we will have sent an additional unsolicited message. So presently there's 14 showing. Take it back to 10. We've sent an additional unsolicited message because we made a class 1 event. If I change the state of analog input number 2, even if I make it change by more than 10, there's no additional unsolicited message. There's an additional event sitting here. Next time the host polls us for unread events, we see those events disappear. So that event wasn't unsolicited, it was sent because the host requested it. So here we've got our DNP operating. We've not associated any of these points to the RTU's physical I/O, but let's now do that just so we can make our demonstration a bit snappier. I have some switches and pots connected to my RTU, so I can demonstrate a few more things by doing that. So let's go to the RTU32, select RTU32 I/O. I'm going to find out what module setup I have by uploading the RTU32M modules. So I have a power supply, a digital input, analog input, digital output, analog output. So I have a nice mix of modules here. I can say OK to that. And we could go to this digital module and we could associate those binary inputs that we have here to this module. I have to click away and come back, and we see that those have been updated. I need to change their channel number. I can right click and iterate those from 0. So now I have we already know this works as a DNP point, but now I've associated it to the first channel of this digital input module. And I'm going to do the same thing to the analog input over here. Drag those on, iterate those channels, digital outs, and I happen to only have a 2-channel module, so let's just take 2 of those analog output channels, make that a 1. And my analog inputs are set up for 0 to 10 volts, and they're going to return 0 to 65,000. Remember, we've set our value at 10 that it has to change by, so I might actually apply some scaling to this. Let's make these represent 0 to 10,000. Oops, should have done them all. Here we go. Doesn't matter. Let's make them look the same. So my first 4 pots that I have connected here will work on 0 to 10,000. We can load this configuration into the RTU. And let's see that it's working, that I changed the state of my digitals. Let's put them all off. I can wiggle my analog pots and I get my 0 to 10,000 happening. So all 4 of my pots are working. And if I write to my DNP outputs, we expect these to work. So we should have slightly different behavior now. Let's shrink this back down a little bit so we can just see our, so here's my analog values. I'll change my pot. We see that change. I come up here and I change my digital value and get my clear skater. Just minimize this. And I want to change the state of my digital, and we see that occurring. Up here we see the analog value change. So if I turn my first pot, which is my analog 0, there are no events being recorded. So I have to wait 30 seconds to see that value change, because that's when my next class 0 pole occurs. Down the bottom here we actually have the time, so we're not going to see that change for another 10 seconds till we get to the top of the minute. So we'll be there any moment now. So now we'd have had a class 0 pole and we see that value change. Now I do have some trends here that just show that concept a little better. So let's just zoom into the trend page a little more. And as I turn my analog value, we just change the range to be automatic. So we're actually moving this between 0 and 10,000. Now this looks very snappy. I can even get my sine wave starting to occur. But if we zoom in, we will actually see that see all those little markers? Every one of those is a time-stamped event that my RTU has generated. So we'll just move it again, just move it a bit slower, but you can see how many events the RTU is creating. So as nice as my trends look, every one of those is being unsolicited as my class 1 event. If I go to the next pot and do something similar, see there's a slight lag when I make a change. It's because we made this one a Class 2 event, and there has to be, I think it was 5 events before it gets unsolicited. If I go to the next guy, just depending, see how there's a little lag before things, but then they get backfilled. So the Class 3 events, we had different rules again. Now the event reporting is easy to see when we look at the digitals. So let's zoom in a little bit. If I change the state of my channel 1, which was a Class 1 event, we see it happening straight away. Let's go back and revisit those rules. What were the rules? They were living here in the static data, and we said that Class 1 events are sent as soon as there is one unread event, Class 2, 5, or if they are 15 seconds old. But remember, my SCADA host is currently polling this RTU every 10 seconds, so we're going to change that. So instead of requesting event data so quickly, we will slow down the integrity poll to 60 seconds, and we'll slow down the event poll to 30 seconds. And that will allow our data to sit and be buffered in the RTU for a little longer. So we still expect a Class 1 event to go straight away, but we expect a Class 2 event to, if I only make 2 changes, we will have to wait until the 30-second event poll occurs. Now we're currently at 25, 26, so we'll not find out about those Class 2 events until the event poll occurs. But when it did occur, notice this is time now, it actually occurred back in time. So we've still got 20 seconds until the next event, unless I make more than 5 changes on that Class 2 event. So if I make them fast, they actually start appearing to come through straight away. I'll make 2 more, and they're going to sit there until we get to the top of the minute, and we then backfilled them again. So just to go back and look at that, why is it behaving like that? Because I configured that channel to be a Class 2 event, and the rules are there need to be 5 unread Class 2 events, or if they are older than 15 seconds, they will be unsolicited. So as soon as I start making a significant amount of changes, they get unsolicited. So if I make 3 changes of state, that's 6 events. 1, 2, 3. So they get unsolicited. If I just go 1, 2, I haven't made enough, and we'll have to wait till we get to the point where the events are either 15 seconds old or the poll occurs. And the poll's occurred now, but it went back and got those events for me. I'll make some slower changes of state. So it's not until there's been 5 changes of state that they get reported. Remember, the Class 3 events will move to the next channel, so I've got my 0, 1, 2, my Class 3 events. What did we say for Class 3 events? We said they have to either be 50 seconds old or there's more than 10 of them. So I really have to start making lots of changes before we see those. So 5 changes of state makes my 10 events. We get them. And if I was to pull out the communications link to my RTU, so I've disconnected, I'm now making 1 Class 1 event, 2 lots of Class 2 events, 3 lots of Class 3 events, So nothing came through. We're going to plug back in, and ClearScader has now called this RTU once it re-established a connection, and I got back my 1 class 1, my 2 class 2s, and my 3 class 3s. So we also proved that we could recover from a comms failure. So let's just look at this once more. So we're managing the application layer rules in the field bus configurator. We're managing the rules for each point in the DNP profile. So what is the class of the point, the type of the point number, and the event reporting rules, the thresholds, and if we put debounce on digitals, we manage that in here. So that's a little introduction to DNP3. We've proved that we've connected it to ClearScader. We did some little examples of how we manage event reporting. I hope that's enough to get you started. Thank you.